it is section 7.3.3 LDA for multiple classes. Now we'll consider general C classes rather than just two. So we are now seeking C-1 projections by means of C-1 projection vectors. W is a collection of column vectors. Each one is a projection vector. A point is projected, then we have a scalar, so that a point is projected with the collection of projection vectors, then it will make a vector in C-1 dimensions. Now the theta metric has n columns, so each column represents a theta point. Then after projection, z must be in C-1 by n dimensions. Now we'll try to formulate the objective function for C classes and try to solve it. Here we start with a recall. For two classes, the within class scatter metric was computed along with this formula, and Sk is defined exactly in this way. So for within class scatter metric, it's a simple generalization. And there's rather than cases from 1 to 2, we are adding them from 1 to C. A simple expansion. For a between class scatter metric, and we have to do a little bit differently. And for two classes, the between class scatter metric was defined in this way. Now, for multiple classes, we use mu, that is the mean of all classes, is mean of all points. And now for individual mean, mu k minus mu is used for this outer product. And then in summation, now here, now weighted summation is made. Okay, SB for multiple classes is a little bit different from now for two classes. But anyway, basically, they are the same, quite similar. Okay, with this definition for now within class and between class scatter matrices, we can now formulate the objective function in this way. Now we have to maximize this quotient. And to solve this maximum problem, we may use calculus technique, and then we can reach at this formula, SW inverse SB. So that for this metric, we have to find the eigenvalues and eigenvectors. But now this one is really now coming back to the quite similar problem as for two classes. Okay, so the collection of eigenvectors will become the transformation metric. Here W star, the optimum projection metric, is the collection of eigenvectors, C-1 eigenvectors. But here the metric is in d by d dimensions, but we need only C-1 eigenvectors. Okay, and of course over there the maximum of JW is the same as the largest eigenvalue. Okay, now for this mathematics, we'll try to simulate one example. Okay, let's generate a synthetic data set for the LDA transformation, and each class has 500 points. First, we make uniform points, and by using Box-Miller approach, we try to convert it to normal distribution. And here, by using some torture, covariance torture, and translation, we try to make three different the classes. Okay, we may start with this one, and uniformly distributed, and by using here Box-Miller technique, we can get here normally distributed points. And for that one, we try to torture and then move here, torture and move. In that way, we try to find the points in other classes. Okay, here we have code for 3 classes, and in fact I'm using Octave and with the package statistics. Now here we first make randomly 1,000 point and separate half and half, and so that one is x coordinate, the other one is y coordinates. And by using Box-Miller method, we try to make it normally distributed, so that that one is made. Now it is a little bit moved, but anyway, here once it is on the origin, then that is exactly output of the Box-Miller method. Okay, here now we are choosing the center, and that is a covariance metric, and a metric is given, is used for now the torture. And by using the information here, x1 is made, so we say that that is denormalized. So that originally x is normalized, so that now move and torture. Okay, so again, by using x with different center and different torture, you can get here now another set, and then again, along with another center and another the covariance metric, you can make another set. So we have a 30 set. Okay, here now we have a 30 class data set, and from now on we try to follow the mathematics. Now count the number point in each class and try to get mean, and now this is global mean, and then within class scatter metric is now made by using covariance, the command, and added. So that is within class scatter metric. For between class scatter metric, and now exactly here we make that outer product, and with the weight and number of points, and here we add them for between class scatter metric. And here inverse of SW and SB, and try to find the eigenvalues and eigenvectors. So we assigned here, and once eigenvalue, so that it is sorting basically. Now the W1 is assigned for the largest eigenvalue. Okay, and here we now try to see the result with visualization. So the major part of the code is from here to there. The earlier portion is now making the data set, and then major part of the code is this one, and this is a visualization. Denormalize, that is now for given here the covariance metric. Now find the eigenvalues and an eigenvector so that here we make that scaling metric, and then it is multiplied. So for the point it is multiplied so that it is tortured, and then here after torturing, now mu is basically added, so it's translation. Okay, now this is figuring part. It's somewhat complicated, but now I try to make the picture here and also add some text so that it's a bit long, but anyway, it's not so much complicated. Okay, now here that is output, and this is a global center, and these are the mean of each class, and this one is now W1 and correspond to largest eigenvalue. Of course, over there are 3 classes. Now we have W1 and W2. So that is W1, that is W2. And here that is first projection vector, and that is second projection vector, and the corresponding eigenvalues are given here. Now, along with this W1 and W2, the data can be projected. And then we can see here now that is now green colored class and red and blue. So you can see here projected values in the W1 direction. That is now in W2 direction. So combining these two projections, now the projected data has 2 dimensions. And original data is in 2 dimensions. Each point has 2 components. We start with a point on the plane. But even though the point is higher dimension, and D is much larger than 2, but after projection, is the projected point is in 2 dimension. Okay, so always projected into C-1 dimensions. Okay, now if you are trying to use this projection for classification, then for the first direction, it has a bit discriminatory the characteristics so that it'll be working well. Okay. Okay, that's the end of part 3. We'll continue on the last part of the section.